Okay, if we can sit down, we're ready to start the next talk. We have Alex and Kostya from Google's office in Moscow talking about their work on the sanitizers in LLVM.
Hi everyone, I'm Alex, and I and Kostya today will talk about the new features in AddressSanitizer tool, about the stuff we're currently working on, and about different problems we encounter. So here's the agenda of the talk. First of all, I'll quickly remind you what AddressSanitizer is and how it works in a nutshell. Then we'll describe the new features that we have, namely the initialization order checker, the stack use after scope and stack use after return detector, and the built-in memory leak detector. And we'll describe you what status of these issues, of these checkers are. Then we'll share our experience of running the Linux kernel under AddressSanitizer and the bugs we found. We'll talk over some miscellaneous issues such as compile time regressions, the new set of Intel MPX instructions, and the problems we have with instrumenting inline assembly, and why we desire to rebuild the whole world, but specifically the system libraries with our tools. And we invite you to BOF session at 2 p.m. today if you have questions or if you want to share your experience or for any other issues that you are interested in. So first of all, what is AddressSanitizer? It's a dynamic testing tool which finds memory bugs pretty common in C++ programs. First of all, it finds buffer overflows for all kinds of user memory, that is for heap memory, dynamically allocated it finds buffer overflows on stack variables and on global variables. And we detect the cases of use-after-free when a program accesses the already deallocated memory. ASan is 2.5 years old, and we found thousands of bugs in all kinds of code, in Google code, in many open source projects such as Chromium and all kinds of third-party libraries, of course, including LLVM itself. AddressSanitizer, as other tools that we develop, consists of two parts. It consists of instrumentation pass, LLVM instrumentation pass, which runs in backend, and of standalone runtime library, which resides in compiler RT repository and which is linked into the final executable. The average slowdown of the program built with AddressSanitizer is about 2x, but that certainly depends on the job that program does. And of course, there is some memory overhead, which is more difficult to measure. It can vary from 1.5x to like 3x or something. And the program uses slightly more, more stack memory, of course. ASan is available for all LLVM users and is included in LLVM releases since LLVM 3.1. And in fact, it's also a part of GCC now. Of course, the GCC has different instrumentation paths, has different compiler instrumentation, but the runtime library is pretty much the same. And it's available since GCC 4.8. We develop another dynamic testing tools as well, ThreadSanitizer, which finds data races in C++ and Go, and MemorySanitizer, which finds the uses of initialized memory. All of these tools are using the same strategy. That is, all of them consist of compiler instrumentation, paths, and the runtime library, which share a lot of code. So how does ASan work in a nutshell? Basically, all of the sanitizers use the concept of shadow memory, where we map, for ASan specifically, we map 8 bytes of each aligned 8-byte chunk of application memory to a 1 byte of shadow memory. And the shadow memory stores the information about what bytes of the original application memory are addressable and what bytes are not. To detect buffer overflows, we insert red zones around user memory chunks. That is, we replace the system allocator and insert the red zones to the left and to the right of each dynamically allocated chunk. We modify the stack frame of each function, and we insert the red zones between local variables. And we modify the global variables and also insert red zones between the global variables. Then we, and to find the use-after-free errors, we don't immediately deallocate the memory, which user called free on, but we store it in the kernel for some time so that we'll find out if the user accesses the deallocated memory soon after he calls delete on it. To detect, well, we know which memory is addressable and which memory is not, and we store this information in shadow, and we call that, we use the term poisoning, so that when we call the shadow memory poisoned if it has the value, which means that the original memory can't be accessed. Our instrumentation pass does a lot of job, but the main thing is that it injects checks for each load and store from application memory. And before we perform the actual load and store requested by the program, we check the corresponding shadow memory value, and if it's okay, then we allow the store or load, and if it's not, if the shadow memory is poisoned, then we crash and print an error report. Pretty much all of the ASan error reports are fatal. That means that we can't continue the program if we detect an error. So here's an example of a use-after-free report to just show you what ASan error reports look like. We allocate a buffer, then we immediately deallocate it and access. And you can see that in this case, the ASan report is the most verbose. We print all three stack traces. We print the stack trace of a place where the actual error happens in blue. We print the place where we deallocated the memory and where we allocated it initially. So this means that we remember the stack traces of each allocation and deallocation made by the user. So now we'll talk about the new features of AddressSanitizer, which don't relate to buffer overflows. And the first of this feature is the checking for initialization order problems. Global variables is bad in C++ in many ways, but one of the specific errors that we're trying to find out is initialization-order-fiasco. That is, the order in which the initialization order of globals from different source files or translation units is unspecified. That means that if, in this example, the dynamic initializers from i1.cc are run first, then A will be equal to 0 and will return 0. But on the other hand, if i2.cc will be initialized first, then B will be equal to 1 to 3, and we'll copy this value to A, and our program will return a different result, which is probably not what we intended to do. You can actually check this. The program will return different results depending on the order in which you will specify the source files in your compiler invocation line. So if you build this program with AddressSanitizer by -sanitizer clause address flag, and you specify a runtime option before running it using the ASan options environment variable, you'll see an error report, and ASan will actually show you that when you initialize the variable from i1.cc, you're actually accessing the global variable from another module, and it's a fatal error, and the program crashes at this point. So how does we do this? First of all, we need to know which globals are dynamically initialized and which are not, which are constants, or zero initialized or so. The front end certainly knows this information, and it simply passes this data to the ASan instrumentation pass using the metadata, so that the clan emits a metadata node which lists all the dynamically initialized globals in each module, so that ASan knows about them. And then our instrumentation module insert a call into ASan runtime, which will describe every global in each translation, in each module, in each translation unit. For each global, we want to know its address, its size, and which translation unit it comes from, and whether it has or it doesn't have a dynamic initializer. For example, we use this information to actually poison the shadow memory for red zones around globals in runtime. But we also now know in runtime which globals come from which modules, which will be initialized dynamically and which are not. So that is, we register all the globals before running any initializers in the user program. And then we actually inject 2 more function calls into ASan runtime when we're doing an initialization. That is, if you have multiple functions that initialize the globals, like 66 global var init or so, which are emitted by clang and then eventually go into the binary, we insert 2 function calls before and after each dynamic initialization block from a module, so that if we are between these 2 function calls, we assume that we are running a dynamic initialization of translation unit with module name. And it means that we essentially forbid the access to globals from any other translation units between these 2 function calls, between before dynamic init and after dynamic init. We implement this by simply poisoning the values of shadow memory. That is, when we call before dynamic init, we poison the shadow memory for all globals from another translation units. And when we run after dynamic init, we unpoison all the memory for all the globals, so that they are fine to access now. In fact, there are 2 modes in which initialization order checker runs, and the default mode and the strict mode. And they differ in the strategy which we use in before dynamic init. In the default mode, we poison the shadow memory only for the globals which are not yet initialized, so that we forbid the access to globals which are not yet initialized and come from a different module. But in the strict mode, we forbid the access to any global from any other translation unit, regardless of whether it was initialized already or it wasn't. The first mode finds the actual errors that happens in your program, while the second mode is more useful, and because it finds any potential errors that may happen regardless of the order in which the initializers for your units actually run. Here I specified that the second mode has false positives, but the example in fact show the false positives for both modes. That means we have some struct foo, and it's written in such a style that you may, well, kind of safely define a global variable of type foo in one module, and then you can call foo.get from another module. And it turns out that it will still be initialized and will be used kind of properly. So that even though you can access the structure like safely, even despite the fact that its constructor hasn't yet run. There are simple examples of this. For example, many implementations of such simple objects as mutex are designed in such a way that they have a constructor which is a no-op, which does nothing, but you can still access the mutex if it's not before its constructor has actually executed, so it's fine. Unfortunately, we'll report the error in this case because, I mean, it's technically initialization of the problem. You access the objects before its constructor has run, but in fact, it's safe. And now we go to the status. Init-order-fiasco checker is off by default due to the reasons I mentioned, because we sometimes produce false positives. That's the thing which we don't usually tolerate in ASan. So a user can fight with them by manually blacklisting either GOT variables or blacklisting them by type names or something like this. But it still requires some manual work. However, it works fine on Linux. It doesn't work on Mac because we have to register all the globals before from all the modules before we run initializers from each module. On Linux, we can use priorities in constructors, but we don't do this on Mac. However, even though it's off by default, we still find this functionality pretty useful. For example, it's on in the strict mode for Google code, and it found hundreds of issues. And we use it as some intermediate step between like the wild code base and the code base which uses no global variables at all, which is compiled with -w global constructors flag. If your code base is huge enough, it may take considerable effort to rewrite in such a case that you don't have global variables. But if you have a checker, you may just fix the actual problems that may cause. And this checker is good in the sense that, unlike other ASan problems, which ASan detects only when they actually happen, when you actually do a buffer overflow, init-order checker finds the potential problems. It finds the code that may break if you will refactor it, if you will move one source, the code from one source to another, or move source files between shared libraries or executable, or specifically when you suddenly decide to compile your code with LTO. Because if you compile the code with LTO, all the code is like merged together in one module, all the globals are intermixed, and you have a completely different initialization order that you have originally. So it would be good to find problems before running it. Another error we are trying to find is the stack use after scope error, which means the access to the local variable which has already went out of scope, like in this example. It works, you need to pass an additional compiler flag to turn this mode on, and in this case, ASan will print a stack with an error report and will describe the frame and the variable which are problematic. We find this type of error especially interesting because the code may work fine and you may access the variables after they go out of scope, and the code will work fine as long as your compiler is stupid enough. Because if your compiler is smart and you do optimizations, it may decide to reuse the same stack slot for multiple variables which have non-overlapping scopes. And then suddenly you're in problem, and this is hard to debug. So it would be good to catch this beforehand with a use after scope. Just a couple of words about how we implement this. We rely on LLVM.lifetime intrinsics, which should be emitted by frontend or by inlining passes, some such. When the lifetime of variable starts, we make it addressable by unpoisoning the memory. When the lifetime ends, we make it unaddressable by poisoning the shadow memory. We need to do the first thing because each variable can go in and out of scope multiple times if, for example, it's defined inside the for loop. So we have to poison and unpoison memory for it constantly. Unfortunately, there's much more work to do, so it's still a prototype. First of all, clan doesn't always emit lifetime intrinsics when we want it to. For example, it doesn't emit lifetime intrinsics for temporaries. It does it currently only for named variables, I believe. And we want to catch use of the scope bugs on temporaries. We still need to use a static analysis to avoid calling expensive runtime functions for each variable when we can prove statically that it's used fine. And of course, we want to bundle this check with a very similar error, the stack use after return error, which will be discussed just now. And so I'll give the word to Kostya to talk about it. Thank you.
Thank you, Alexey. My name is Kostya, and I will talk about a couple more new features in AddressSanitizer and some miscellaneous stuff. So use after return is indeed very similar to use after scope, with the difference that the scope is the function itself. So we're trying to find bugs where you take a pointer to a local variable, you return from a function, and you continue using that local variable, which now belongs to someone else's stack. This actually happens often from some different thread, for example, which is a nightmare to debug. So in this example, all you need is to compile with the regular AddressSanitizer switch and then run with a special runtime option. It will show you where the access happened, and it will show you where the local variable have been created. How does this work? When we instrument a function, we keep the original frame, which was there from the C language, but we also create a pointer which we call fake frame, which comes from a specialized malloc-like thread local allocator. I'll talk about it later. And at the function exit, we actually call stack free on that fake pointer. And here's how it works. So this stack malloc and stack free are things very similar to malloc, but first of all, they're thread local. They don't care about threads, and they have to be extremely fast. Another requirement for these two functions is that they actually have to implement quarantine, so that if something is freed, it is not reused for the longest period of time possible. Internally, it uses a fixed size, a single fixed size M-mapped buffer. So if you actually have a very deep recursion, this buffer can be exhausted, and the malloc implementation cannot have anything to return. In this case, it actually returns the original frame, so we just not catch any bug in a very, very deep recursion. But this allows us to be very efficient. Yet another feature which appeared in AddressSanitizer recently is leak detection. Well, everyone knows here about leaks, and here is the simplest example I could come with. We allocate memory, we lose a pointer to it, and we never deallocate it. The same thing here, we compile with AddressSanitizer and run with a special switch. It will tell you how many leaks you have and where the memory which has been leaked was allocated. So we're not doing any rocket science here, and the tool is very similar to many other leak detectors on the market, like TSan, leak detector, valgrind, many others. But what we do differently, we're actually much faster than any other tool we know of. We have no extra overhead on top of AddressSanitizer at runtime, and we have a very tiny overhead at shutdown time when we actually need to report leaks if there are any. The tool is based on the memory allocator, which is shared between AddressSanitizer, memory sanitizer, and thread sanitizer, and I will talk about it shortly. This allows us to bundle the leak detection with any of the three tools, or use leak detection as a standalone tool. And currently we support only two modes, bundled with ASan or standalone. The key implementation detail of the leak detector is the function which we call stop the world, which creates a special thread outside of the process thread group, freezes all the other threads, and executes some special callback. Unfortunately, today we have it only on Linux, so the leak detection functionality today is available only for Linux. A couple of words about the allocator, which we use in the leak detection tool. First of all, it is absolutely full implementation of malloc-free new delete API. Internally, it uses thread local caches similar to TSan, so it works fine if you have thousands of threads. The difference between our malloc and many other mallocs is that it has extra features that are required for all of the three tools. And the major feature is that we need to associate some special metadata with every chunk of heap allocated memory. Examples of metadata we store, like stack trace when the malloc of free has happened. And different tools have other special metadata. So for AddressSanitizer, keeping metadata is actually simple because AddressSanitizer heap chunks have red zones at the left and the right, and we use those for storing metadata. But TSan and MSan store metadata in some other place, not adjacent to the memory chunk, and this is important for those tools. And we absolutely must have very fast mapping between an arbitrary user address to a chunk of heap allocated memory, and from a chunk to metadata. And here's how we do it. So the allocator plays dirty tricks with virtual memory. On 64-bit Linux, it pre-allocates 4 terabytes of virtual memory, splits this at a fixed address, which is important, splits this 4 terabytes into 64 regions of the same size, of course, and each of these regions is used to allocate its own size class chunks. The chunks in every region are allocated left to right, and the metadata associated with the chunks is allocated right to left. The structure of the allocator allows us to have very fast mapping between address, chunk, and metadata, which uses very simple arithmetic instructions and has no locks in it. Let me move to the miscellaneous section, just random grumbling and complaints. Well, this is not complaints, this is good news. So we have AddressSanitizer for Linux kernel today. Unfortunately, it has nothing to do with LLVM except for the name. We currently, our early prototype currently uses GCC thread sanitizer instrumentation for some obscure reasons. The main reason being that the instrumentation for the kernel is a little bit different than we need for the user space. And the runtime library is completely different. It is just part of the kernel malloc implementation. As I said, it's an early prototype, but we already found a dozen bugs and 5 got fixed, maybe 6 today already. We really want to use Clang instead of GCC for better instrumentation and for more features in the kernel. I don't really know the today's status. Last time I checked, we knew that the Clang features, the Clang issues are resolved, but there are some issues in the kernel itself. So if you have some other kernel and want to try AddressSanitizer, and talk to us. So this is a little bit grumbling. Intel has recently uncovered what is called Intel memory protection extensions. This is an upcoming instruction set feature that is supposed to be used for buffer overflow detection. I have a long list of complaints about this thing. First of all, it is slow and uses lots of memory. And if you're interested, I have a very biased comparison wiki page. But this is still very, very much worth supporting in LLVM because it has one feature that AddressSanitizer doesn't have. MPX allows to find inter-object buffer overflows. Like if you have a structure with several buffers, you overflow from one buffer to another buffer, and AddressSanitizer will never catch it. MPX can do it. So I'm very interested in integrating MPX with LLVM in some way. And really, this CPU extension may actually be very fast for some kinds of codes, basically for vector or matrix matrix kind of loops, long loops iterating over simple arrays. This will be perfect for this use case. Another piece of complaints, ASan and also MSan, they create extra control flow in the LLVM IR. And this explodes sometimes some of the optimization passes downstream, mostly in code generators. I have one outstanding example, but there are many more. So the usual issue is that there is some optimization phase that has quadratic algorithm in worst case, and we actually hit this worst case because we create lots of new basic blocks. We currently have a project to recompile all of the libraries in Ubuntu distribution that Chrome depends on. Why would we do it? So for all 3 tools, we have different reasons to do it. For ASan, this is better stack unwinding with frame pointers. Usually libraries are built without frame pointers on Linux. For TSan, this would be catching synchronization done using atomics in the library code. For MSan, this will avoid false positives. And for all of the three tools, of course, this is more coverage. Our early experiments already found a few bugs in like standard Linux libraries, so we're going to extend it. Our current status is that we can build about 50 libraries used by Chromium. This is what we care most about today. But the build system is often hairy and the code sometimes not very Clang friendly, so help is welcome always. More or less for the same reasons as libraries, we also want to instrument assembler. For MSan, it is absolutely critical. For example, in some of the standard Linux C++ headers, we have assembler to implement something like memset, absolutely crazy, and we choke on it. Also, often depend on optimized libraries like OpenSSL, libgpeg, turbo, or something. And again, all tools, including AddressSanitizer, will benefit from instrumenting assembler. We have a few ideas which we are going to try in the coming months. First is a simple pattern matching for simple things like FD0 in the Linux headers, and some other things using MC layer or separate MC pass. And if you have ideas, please come to us and tell us how to do it, or tell us how not to do it. So to summarize our talk, AddressSanitizer keeps adding new features. We have init-order-fiasco. It is done. We're using it very extensively on Linux. We have use-after-scope feature, which is still work in progress, and there is some work to be done in Clang as well. We have stack use-after-return, which we call beta, but we already use it heavily. We found many dozens of bugs. And we have a leak detector, which just works on Linux. We still have lots of work to do: libraries, assembler, kernel, Intel MPX, compile time. And of course, ASan is well done for Linux x86-64, and for all other platforms there are some issues. And we keep working on all of those, but yeah, again, help is welcome. This is all we have, and we're ready to take questions. Thank you.
If you have any questions, put your hand up and I'll bring the mic to you.
Hi, can I give more details on the thread sanitizer and the memory sanitizer? Where are we on those?
So thread sanitizer and memory sanitizer, we call them siblings to AddressSanitizer. They share a lot of code and runtime. Thread sanitizer finds only one kind of bugs, data races. It is much more expensive than AddressSanitizer. It uses more memory and more CPU, but it is very good at finding data races. And I think we already counted about 1,000 data races that it detected in our code. I know that Firefox found at least one bug in some Mozilla code. Memory sanitizer is also a one-bug tool, one kind of bug tool. It finds uses of uninitialized memory. We are very often asked why don't combine AddressSanitizer and memory sanitizer, like valgrind did. And the answer is that if we combine those two tools, we'll get valgrind, which is very slow. And my claim is that separating these two tools is actually what allows us to make these tools fast, both of them. Both of the tools today work only on Linux x86 64-bit. Thread sanitizer is also applicable to the Go language, and the Go variant works on Linux, Mac, and Windows. Is there any plan for Android support? With thread sanitizer, the problem is that it is designed to be 64-bit only. So We now have iPhones based on 64-bit chips, so the chips are out. I have no idea whether Android will go the same path, but if it does, we will do the 64-bit ARM threat sanitizer.
Any other questions? Going once. Going twice. Oh.
What's so specific about x86, or rather, what needs to be done for ARM if you want to port the similar solution?
About which tool are you asking?
AddressSanitizer?
AddressSanitizer works on ARM well.
Okay, so you mentioned that there is some limitation. It works only on x86 for one of the tools.
That's Threat Sanitizer. Threat Sanitizer really needs 64-bit atomic loads and a lot of virtual memory. AddressSanitizer doesn't care about it, and it works well for ARM. We are actually using it on ARM. And we've been told about AddressSanitizer on Spark, PowerPC, MIPS, and something else exotic.
I had one more question/comment. Are you guys aware that the Linux Foundation maintains patches for Linux kernel to build with LLVM? And my understanding is at this point, there are no patches required for LLVM, and there are some patches obviously required on the kernel side. So I'll be happy to give you contacts, and it'll be interesting to see if we can find more issues using the AddressSanitizer on the kernel using LLVM. I know that they do this for ARM, and they are able to successfully build the tip of the kernel with the tip of LLVM.
Good, thank you. We of course are interested in having all the fixes in the kernel trunk or whatever, in the Linus section. But if there are patches somewhere, we'll certainly try them.
Any more questions? Okay, well, thank you very much. Thank you, Kostya. Thank you, Alex.
Thank you.